Welcome to our work on detecting permissible driving routes in radar using weak audio supervision. The underlying focus of this work is on the use of radar as the main sensor for a perception system. Radar provides us with a 360-degree understanding of a given environment with a range of hundreds of meters. Most importantly, it can do this while being robust to the changing appearance of scenes due to any number of factors such as darkness at night, fog, or snow. This allows for invariance to all environmental conditions that a deployed system might experience. For this reason, radar has been proposed for the tasks of ego motion estimation and localization. However, it is rarely used for more general scene understanding tasks. One example of such a task is drivable surface segmentation, or rather permissible route identification. This task has been heavily investigated using vision or LiDAR, but has not been for radar despite its inherent advantages in its robustness to many environmental conditions. In this work, we show how drivable route segmentation can be performed by radar. This work is in line with the partnership between the Oxford Robotics Institute and Navtech Radar to develop both the hardware and software required for all-weather sensing with radar. On the right, a Navtech radar can be seen fitted atop our Oxford Robotics Institute Range Rover. So in terms of what our radar data looks like, here we compare camera data and radar data both collected in the park in Oxford. As you can see, there's a significant difference in field of view and range that comes with radar. In this example, the camera stream is subject to some fairly large changes in illumination due to the low sun, and is unable to see an appropriate drivable surface, i.e. a path, due to a lack of range and field of view. On the other hand, in the radar stream, we can clearly see a path to the right of centre in the scans that is only not visible when occluded by large trees. This shows that, given the right methodology, it should be possible to segment drivable surfaces using radar. In order to train a system to segment the desired parts of a scan, we must first label the scans. It would, however, be very time-consuming to label thousands of scans by hand, and so we would like to generate these labels automatically somehow. Our solution is to use a data stream from another sensor to label the scans for us, also known as weak supervision. We choose to use recorded audio for this task. From audio, it's possible to extract information about the ground a given mobile system is travelling over, as the interaction between the terrain and its wheels or feet has a distinctive audio signature. For this reason, we can collect an audio training dataset and train a classifier to classify the terrain a given system is travelling over. This is attractive as the audio signature is much less affected by bad lighting or weather than cameras would be. Datasets of audio are also very easy to label, as we'll discuss later on. So how exactly do we use a one-dimensional audio signal to label a set of 2D radar scans? We know what type of terrain the mobile system is travelling over at any one time by classifying the audio stream, but we can also track where the system has traversed in the environment by using a combination of GPS and visual odometry. So we know where the system has been and at what times, and also we know what the terrains were at any given time. By combining these, we get a terrain-labeled trajectory of the system in the environment. This labeled trajectory can then be superimposed over each scan in order to label them. To carry out this plan, the following experimental setup was used. The mobile platform used was the ClearPath Husky robot. We fitted a Navtech frequency-modulated continuous wave radar on the top. This radar can be operated in both a long-range and short-range mode, and we collect data for training and testing in both these modes. We fitted two omnidirectional microphones by the wheels to capture the interaction between the wheels and the terrain. We have a stereo camera in order to estimate our ego motion with visual odometry. And we used a simple USB GPS receiver in order to alleviate some errors due to drift in visual odometry. So this is an overview of the labeling pipeline we designed. As previously mentioned, we first classify the audio signal based on terrain, and then combine this with the GPS measurements and visual odometry estimates to produce a label for each scan. Seen in more detail, the scan labeler is broken into three subsystems. The most important of these is the extended Kalman filter that we use to fuse the visual odometry estimates and GPS measurements. The output of the Kalman filter is an estimate for both position xy and orientation theta for the robot at each time step. The estimated positions are what are referred to as the robot's trajectory in the environment. The way in which we chose to perform audio classification is through the use of a convolutional neural network classifier. When classifying audio with a CNN, you typically transform the one-dimensional audio signal into a set of two-dimensional time-frequency plots, such as a spectrogram. This works well because CNN classifiers are very good at classifying data with local spatial correlations. And by assuming local spatial correlations in an audio spectrogram, the CNN classifier learns to recognize the temporal correlation of characteristic audio frequencies. In this work, we used gamma tonegrams as audio features because they perform better than the simpler spectrogram and its other variants. Each gamma tonegram is generated from a 0.5 second clip of the original audio signal, meaning that our classifier can classify the train every half second. In order to train a CNN classifier in a supervised manner, we first require a labeled audio dataset. As previously mentioned, this is very straightforward. The reason for this is that audio can be recorded from each terrain class separately, unlike in vision, where each image will contain a number of different classes that each need to be labeled. Since we can record audio from traversing each terrain separately, we can simply label the entire audio signal from each traversal with a label of the terrain it was on. After this, all we need to do is just to generate gamma tonegrams from the audio signals and then randomly combine the different sets to get the final training dataset. So the audio classifier gives us knowledge of what terrain the robot was traversing at each time step. We then have to combine this with knowledge of where the robot was at each time step. We do this in 3 steps. Firstly, we fuse the GPS and visual odometry estimates with a Kalman filter to obtain accurate estimates of both position XY and orientation theta of the robot at each time step. The reason we fuse GPS measurements with our visual odometry is that it allows us to mitigate the effects of drift in the visual odometry estimates. It's also worth noting that the output estimated positions XY we refer to as trajectories. After this, we take the trajectory and we label it. And this can be done very simply, as each terrain classification from the audio has a timestamp. We can then just associate the position with the classification with the closest timestamp in order to label it. Then when the trajectory is labelled, it has to be fitted to each scan individually. This is because the labelled trajectory is in the global reference frame, whereas the radar scan is captured in the robot's local reference frame. To fit the labels to the scans, we look at the timestamp of the scan and find out where it was in the trajectory. As the robot is naturally in the center of the radar scan, as it was captured by it, we can then match the trajectory of the scan by putting the position at the timestamp in the center. After this, we simply have to adjust the orientation of the trajectory overlaid on the scan using the orientation estimates. And then after this, all we have to do is scale appropriately. Here we show a radar scan next to the satellite imagery for the same area, and hopefully you can see some similarity. For example, here you can see the paths illustrated in the radar scan. And here's an example of a labeled scan from one of our training runs. We performed 2 training runs for both the long range and short range setting in the radar. For this training run, you can see that we've chosen to label only one of the paths in the scan. And the reason for this is that we think it's inevitable that you won't be able to traverse every terrain of interest in a set of radar scans, since they just cover such an enormous area. And for this reason, we've made the labeling deliberately sparse in order to ensure that the training procedure can cope with the inevitable sparsity of the labeling approach. When designing the training procedure, we made the observation that when the segmentation network is trained on sparse data, the network eventually overfits to the sparsity and does not generalize effectively. Looking at these examples, this means that it will not segment the path on the right, as it was not initially labeled. The first step to overcoming this is significant data augmentation that includes cropping, rotation, and elastic deformation to generalize the appearance of the paths. And then secondly, a curriculum was devised using a label refinery technique, whereby the initial labels are augmented by the network in order to improve performance. The second and final stage of the curriculum is then to fine-tune the network on the more comprehensive set of labels generated by the network. As you can see after the final stage, that the path on the right is well segmented, having not been initially labelled by the labelling pipeline. The motivation for training neural networks in a curriculum stems from the idea that neural networks often perform better when they are presented with the most understandable examples first. In our case, the problem of path segmentation is most easily understood when the receptive field of the network is small with respect to the scan. In other words, we initially present the network with small crops of the original scan, which removes some of the complexity of the scene context. The result of this is the network segments paths well, despite the incompleteness of the labeling, unlike what happens when you try to train on the scan as a whole. The network from stage 1 is then well suited to adding additional labels to the dataset by segmenting the scan one small crop at a time. As previously mentioned, these additional labels are taken as ground truth and then used to fine-tune the network to segment the whole scan in one pass, i.e. without the need for cropping. Here we see the results of a robot traversing an unseen test environment. This demonstrates that the system can segment a drivable route that's behind occluding trees at a range of hundreds of meters and with a 360-degree field of view. We note that there are some temporal artifacts that we believe will be easily removed by enforcing consistency in the predictions across time. Here we have some segmentation results from another set of unseen test data in the short-range setting. The images have been post-processed such that correct classifications are seen in red and incorrect classifications are seen in yellow. Besides the aforementioned temporal artifacts, we note that there are some other ways in which the system can fail. This slide shows some failures from both the long and short-range settings. The first can be seen in I and M, where thin objects cast a radar shadow that looks somewhat like a path, leading to misclassification. The second is seen in K and O, where a vertical disjoint is seen in the radar scan, which is caused by motion during the scan formation process. As you can see, this disjoint is then falsely classified as a path, again seen in yellow. This artifact can, however, be dealt with by motion correction. If any of this has sparked an interest, we suggest reading our paper in more detail. The second paper listed here also goes into a deeper dive on audio classification using convolutional neural networks, if that's of any interest. Thanks for listening, and if you have any questions about this work, or radar as a sensor more generally, feel free to get in touch. We hope you've had a great virtual ITSC.